Okay, fuel injector driver design, section 17. Purpose of this section is to get you used to looking at the waveforms that you're going to see with fuel injectors, both voltage waveforms and current waveforms. There are two different designs, two main types of computer drivers, peak and hold and saturated switch. And basically, as we go through this, what you're going to see, I'll pull up the picture real quick. What we're going to see is a peak and hold waveform would look like this. You see a single voltage spike up here, looking up here, and the ramp for the current looks like this, as opposed to a peak and hold where you see we have two spikes, and the ramp looks completely different. So the idea really with this is that you understand the differences in the designs to make an accurate diagnosis within the waveform. There's a lot of things we can look at in the waveform. All right, so with all injection, the speed at which an injector opens is important to the engineer. So when they calculate the fuel map and they do everything they need to do and take all your air measurements from all your sensors and then design a certain injector that's going to have the right volume with the right fuel pressure behind it, time in the injector opening is also something that the engineers have played around with. How fast in time does that electrical injector open? And so that's kind of where these different designs came from, the peak and hold, saturated switch. And so I have some of that listed here. Some other things that play a factor in the time that that injector opens would be system voltage. So if you think about an engine that's cranking as opposed to an engine that's running, it's not uncommon to see a 4-volt difference in system voltage. So if you're cranking the engine over, the starter has a lot of amperage and system voltage is low in just from cranking, well, the injector on time is going to be longer just to account for the lower system voltage. So computer not only controls the injectors based on, of course, cranking and temperature and all that stuff, but it's also looking at battery voltage for battery voltage corrections. So there's always some type of ignition sense circuit on a computer, and that's one of the things it's used for. So variations in system voltage, the injector resistance and current flow, how fast the magnetic field builds, these are all just things that need to be accounted for the fuel injector itself. Size and flow rate, that's a big one right here. Size and flow rate. Yeah, you definitely don't want to just put any injector in the car. It needs to be sized for that car. Starting with just a generic picture of these driver designs, saturated switch, peak and hold. It's really about total circuit resistance here and how we're controlling the current flow through the injector is where these terms come from. When we use the term saturated switch, there's really no limit in the driver in the computer, as you can see in these two pictures. These are both saturated switch, that they're just on-off type drivers. We're not limiting the current flow with the driver. We'll turn the driver on, we'll let the current travel through the winding of the injector, and it's the resistance of the winding of the injector itself that's going to limit the current flow. Generally speaking, our saturated switch circuits are 12 plus ohms of resistance. So the resistance itself is going to limit the current flow. Saturated switch meaning we'll just turn it on, let the magnetic field build to saturation, and then we'll turn it off. We don't need to limit the current flow. That's where the term saturated switch comes from. They also call, another name would be a voltage controlled injector. I've heard them called that, voltage control. This is most common, is a saturated switch type fuel injector. And you're going to have one, if you're looking at a voltage waveform, you're going to have one voltage spike. A peak and hold is different. If you look at this internal to the computer or the driver, it's a little bit different of a drawing, but what that's showing is that is showing a driver that is capable of limiting current flow. So this driver kind of throttles, if you want to call it. It controls the amount of current flow through the injector. And generally speaking, these would be 1 to 2 ohms of resistance would be your peak and hold type circuit. So they need some type of current limiting to prevent too much current flow and heat and burning up the winding of the injector. So on a peak and hold, we need to add resistance to the circuit to prevent the system from burning up. Now, why did they do these two designs? Why have they been experimenting with them? Is the time it takes for the fuel injector to mechanically open. So from the moment the transistor turns on to where the magnetic field builds strong enough to where the mechanical piece inside the fuel injector opens, the time they've been experimenting with that. And that's what A and B is in this picture. A would be the transistor turned on, and B would be the moment that the mechanical pintle moved with the fuel injector. And you see that this first design between A and B, so we're just looking at the time between A and B. Again, time between A and B here, and then the time between A and B over here. Honda used this design. This is actually a Honda design from what I've seen, where they use what they call series resistors in front of the fuel injectors. So it's still a high resistance circuit, but they're using a low resistance injector. So it almost looks like low resistance injector here, but this is a low resistance injector here on the peak and hold. What is the difference with Honda is they put a resistor in front of each injector, which combined with the injector itself makes it a high ohm circuit. So the resistor is limiting the current flow on the Hondas. And why they did it that way, as you can see in the picture, the Honda injector opens faster in time than a conventional saturated switch injector with no resistor in front and a high resistance injector itself. That's what they're doing. I'm not the engineer. I didn't make it. I don't understand the whole time thing. Most of the cars are pretty much done. Most of the cars that you're going to work on are done like this. So it's just a time factor that they build into the fuel map, and we need to allow more time for this to occur. But that's where engineers have been changing this over the years. What we saw, what we see on the peak and hold. So we're looking over here. What we see on this peak and hold design is this guy opens the fastest. The time between A and B is the fastest. And the reason it opens so fast is it builds a magnetic field very fast because the current flow is much higher and it's a low resistance coil. Now the problem with that would be when you have longer pulse widths or longer on times, that if you were to turn this design on and just give it a ground for as long as you needed fuel, it would burn up the windings in the fuel injector. So the idea with this one is we'll give it a full ground, allow it to have unlimited current flow for a millisecond or two, and then once the injector mechanically opens, we can weaken the magnetic field and hold it open for a longer period of time. We can hold it open for as long as we want without burning up the winding. That's done by adding resistance to the ground. And that's what this driver is doing, is it's adding resistance on the ground side of that circuit. So it's called a peak and hold because we're going to peak the current flow. As noted in this waveform, this is actually a current waveform. And the hold section, which is what you're looking at here, peak and hold. It's similar to a starter solenoid in that it takes a stronger magnetic field to move the solenoid than it does to hold the solenoid. So starter solenoids have pull-in and hold-in windings that on initial crank, before the motor starts to spin up, both windings are energized, and then as the motor spins up, one of them is dropped and the other one holds it and keeps the solenoid engaged. Stronger magnetic field to move a component, weaker magnetic field to hold it in its place. Okay, so with this design, what you'll have is two spikes because this is the end of the peak section and this is the end of the hold section. So we really have two magnetic field collapses on this design. And ultimately, that's the most important thing when it comes to this, because we're not the engineers, we're not designing the circuits, but we need to know how to interpret the waveforms. Peak and hold and saturated switch. Now, a warning with this would be if you're energizing fuel injectors. We've talked about this in section 3 in my book, where we talk about output solenoids and transistor drivers, and we went through all kind of tests on how to energize an output, whether it's power or ground side switched, and using a test light to do that, or using a jumper wire safely, as long as you know the polarity. And so I get questions about, people wanting to energize a fuel injector manually. And for the most part, you don't want to do that. First of all, because you can fill the cylinder up with fuel and cause a hydrolock situation. But even more importantly, when it comes to the peak and hold design, if you were to manually energize a peak and hold injector, understand that you would be giving it a full ground the whole time you're energizing it, and you could potentially burn up the winding in that fuel injector. You would not want to manually energize a peak and hold fuel injector for that reason. The computer limits the current to keep the injector winding from burning up. Okay? All right, next page. So let's break down this saturated switch injector. I have two waveforms up here. The red trace is our voltage waveform, and the blue trace is our current waveform. And this is on one fuel injector. Something else you'd want to keep in mind with this picture is my amp probe, my blue trace, my current ramp is this note right here. 100 millivolts equals 1 amp. So I'm using a conversion just to get an idea of the amperage on here. I should have selected on my scope, would have made this a better picture if instead of using a voltage. This is actually a 5 amp scale. I should have just picked the amp probe setting, and then it would have done the conversion for us, and we wouldn't have to do that conversion. But this picture was done with a voltage plus and minus 500. I actually chose that scale over top of the factory setting for an amp probe because I like my zero line. When I do amperage testing, I generally like my zero line off to the bottom of the screen. In case I have my amp probe connected backwards, I'll be able to see a negative amperage. And some of the factory settings, they don't allow you to do that as easily. So that's why I chose it like that. But in any case, 100 millivolts is 1 amp. So my current pattern in this blue trace, you can see at the peak, is around 1 amp. So that's what we're looking at right here. A peak amperage of around 1 amp. That's a saturated switch. When we shot the video on that Chrysler Maserati with injector problems, if you guys remember, we were looking at amperage of around 0.7 of an amp per injector. And we knew that that was okay from doing repetition, knowing at least an idea what they should be drawing. And we said that that was good. So around an amp, just under an amp. So what I'm seeing for the most part really would be about 0.7 to 1.0 amps is probably a better number to go by as far as what should it be when you're looking at a saturated switch fuel injector. All right, so blue trace, red trace, just to give you an idea of where we're doing this check. If you're looking at a fuel injector circuit, what you would have is some type of feed. There would be a fuse. You'd have your fuel injector, and then this would be internal to the computer. Where can we acquire the red trace or the voltage waveform? Only on the control wire. This is the control wire, the wire that goes to the computer. This is the feed wire or power wire. If you want a voltage waveform, which is the red trace, you're only going to see that in this leg of the circuit. You have to be connected to the control wire. Take your meter on a voltage scale, connect it to ground, and you will acquire this red trace. You cannot see the red voltage waveform on the feed side. It's not possible. All you'd see on the feed side of the circuit is a flat line, fixed voltage, battery voltage on the feed side. Now, when it comes to current measurement, which is the blue trace, you can put an amp probe, which is what I'm using, on the feed side or the control side, either one. Amperage can be done on either side of the circuit. Recall that current flow does not change through a simple series circuit. It's the same all the way through. Feed side is going to be the same amperage as the control side. What comes in must come out. Pressure changes, flow does not change. If you can imagine pressure in a garden hose, water flowing out of the hose, the water that's inside the hose is pressurized. The water that leaves the hose is unpressurized, but the flow rate would be the same everywhere you would put some type of flow meter. It wouldn't matter if you put it at the spigot. It wouldn't matter if you put it at the inlet of your house. It wouldn't matter if you caught it in a bucket and measured it. The flow rate would be the same all the way through. So that's what you want to think about with voltage and current. That's kind of nice to remember, because later what we'll be doing is we'll be removing the fuse, installing a fused jumper. It's nice they sell those too, those fuse buddies. They sell those things. Picotech.com, they sell them. Fuse buddy. They're not that expensive. Check it out. You can put an amp probe right here on that fuse buddy, and then what we can do, if that fuse feeds multiple fuel injectors, we can read all of those at the same time. Remember though, we're not looking at voltage when we do it at the fuse box. We're only looking at current flow. Okay, so a little review on voltage and current waveforms. All right. So let's look at this waveform and plug in some stuff. These are things I look for. When I look at fuel injector patterns, these are some characteristics I look for in every waveform. Starting at the red trace over on the left-hand side, I'm showing that this line right here, we're looking right here, should be battery voltage. Understand that what you're looking at is the circuit is off right now. And again, to draw this generic picture, and what I'll do this time is I'll draw the transistor as a switch. So it is a ground side switched transistor. If I'm measuring right here with a voltmeter or a scope, and that switch is open or off that we're looking at right here, the voltage in my control wire is going to be battery voltage. So we'll call it 12 volts, circuit off. Granted, you have a resistor here, which is the injector itself, but no current flow, no voltage drop. So the first thing you can see in a voltage waveform of a fuel injector is you can actually see your feed voltage, and that's what we're looking at again right here. And that number, if you look at this picture, there's 10 volts here. Looks like that's about 12, maybe 13 volts, somewhere in that range, right? If you saw 5 or 6 volts there during this waveform, you have a feed wire problem. You have a voltage problem. So we can look at that first line to tell us battery voltage. The next thing that happens, the switch up here is going to close. So our driver went from open to closed. And so we now gave this circuit a ground, and Kirchhoff's voltage law, all that voltage is going to drop in this circuit, right? So we should go from 12 down to near 0. It's not going to be a perfect ground because wires themselves contain a certain amount of resistance. The block, the wires going back to the battery. So near ground, but what should happen, this line, that's what you're looking at, is a clean straight line. It just switched on. And then the on section down here is where we're focused at. And that should be very near ground voltage. And what that shows is the driver inside the computer has a good ground. Remember that everything that grounds into the computer essentially comes out and grounds to the block. We call those power grounds on a computer. if you saw high voltage on an injector ground, you could potentially have a bad computer ground. There are other causes of that. Shorted injectors, computer trying to protect itself. Some of that we've shot some videos on, where you have higher than normal ground voltage. But that's what you want to see. Now from right here to right here, we call this our injector on time or pulse width. That's the amount of time the injector is spraying. It's the amount of time the circuit's on. At the end of the on time, you notice the transistor turns off. I have listed here as transistors off. Looking right here. And we have this spike. And the spike is actually caused by the collapse of a magnetic field. Anything that has a coil of wire that makes a magnetic field, when you turn it off, you're going to get a voltage spike. One of the things we can look for in the voltage spike is we want to see a minimum of 60 volts. Minimum of 60 volts. And I have that listed up here. Minimum 60 volts. And what that does is that shows you the magnetic field strength of that fuel injector. If it only spiked to 20 volts, what we would say to ourselves is that fuel injector has a weak magnetic field. So the height of the collapse tells us magnetic field strength. Now there's something interesting with this particular one, and it looks like somebody took a pair of scissors and cut off the top of the spike. What you would see instead of this, if there was no Zener diode dumping off the spike, is you would see a spike that would come up and it would peak and come back down. It would literally not look like that. I have a few waveforms in my book and other places that show that. I've seen fuel injectors spike over 120 volts. It's not uncommon to see over 100 volt spike on a fuel injector. But I'm telling you guys to look for a minimum 60. And there's a variable to that. And of course, it's this Zener diode dump off of this spike. And essentially what they do, again, drawing a generic picture, is inside the computer where our transistor is, we'll just draw it as a switch. We'll put a Zener diode right here, put this to ground, and in this case, looks like it's about a 65 volt. And so the breakdown point of this Zener is 65 volts. So if the injector's off, we said already our voltage in this leg of the circuit is blocked by the Zener. It will not go reverse bias. Is 12 volts, 12 to 14 volts, engine running. So that diode has zero effect right now with the circuit off. When the circuit turns on, driver closes, we get a ground. This drops to near zero. So again, this Zener diode is not into play. But as soon as that fuel injector shuts off and this driver opens back up and this magnetic field collapses on here, you're going to get a very large voltage spike in this leg of the circuit. And what that's going to do is it's going to hit this, whatever number that Zener's rated at, it'll hit that number and it'll bleed the rest of it off the ground. And what essentially that was there for is to protect the driver from those large voltage spikes, is what the Zener dump did. And that'll affect your reading. That will affect this reading right here. I'm telling you to look for a minimum 60 volts, but if there's a Zener diode on there, it's going to change that. Okay, question was, as long as this spike has this kind of flat top, and we're not so concerned if it doesn't hit 60, and that is correct. You're going to see in the next picture, let me jump there real quick, in the next picture that these ones are only hitting about 37 volts, and I'm totally okay with that, even though I'm giving you a 60 volt number, because you can see clearly that those are being clipped off. And really, truthfully, what this boils down to is experience and seeing multiple hundreds of injector waveforms and getting used to looking at them. What we should be doing is checking good ones, not just checking bad ones. So when we have, time on our hands, we should, go to our car and connect to the injectors and take a look at what they look like. If the car's running fine and there's no problems, you can be pretty sure the waveform you're looking at is normal. So that's plays into and that is in play here too. Experience. All right, back to this. So minimum 60 volt spike unless there's a zener, dump it off the spike. The next part's really useful. I use this a lot. I actually have a video on this. The title of it is Stuck Open Fuel Injector Case Study. And on this car, we had a single cylinder misfire, and we pulled up the injector waveform. And it's very clear if you watch that video that I am using this pintle hump section as a diagnosis for a stuck closed fuel injector. So what this is mechanical movement through a collapsing magnetic field that actually induces a little voltage kick in the circuit. If you can remember creating voltage with magnetism, we need a magnet, we need motion, we need a conductor. We have all three of those taking place with the pintle closing. There should be a hump right here at the end of that waveform. What that shows you is mechanically that fuel injector is closing. Right? It's one of the main things I use on the Maltec 2 fuel injectors. Maltec 2. Remember the Maltec ones GM made? They all sorted out. Got a couple videos on that too. The Maltec 2s, the redesign, they don't sort out anymore. They just stick mechanically. So again, GM has yet to make a good fuel injector. This is where I focus on those cars with single cylinder misfires. I'll look at that pintle hump and see. All right. So down to the amperage waveform. Let's take a look and plug these numbers in now for the amperage waveform. It's no surprise that when my transistor turns on, I have the beginning of my current flow in the circuit, right? Voltage drop, ground side switched. When the voltage is low, current is flowing, okay? And what we want to see here is we want to see a ramp right away. We don't want to see any straight up lines. And by straight up lines, what I mean is if this waveform looked like this, that would be the beginnings of a shorted injector. Okay? In the 20 years I've been doing this, the only injectors that I see do this are the Maltec ones. GM, right? Early model GM vehicles. Major problem with shorted injectors. That would be a partial short. As they got worse, this line would increase further, and then this, of course, would climb. And I've seen them where they'll pretty much be something like that, which is a completely shorted condition, overloads the driver, causes the car to shut down because they were group-fired systems. But we want to see a ramp. Anything that makes a magnetic field should create a ramp effect. And the reason behind that is counter voltage, counter electromotive force that is being generated by an expanding, moving magnetic field. And again, we have the three things we need to make voltage. We have a magnet, the magnet's moving, and we have a conductor. Are we creating voltage as we're trying to magnetize this injector? And the answer is yes. And that's what causes this ramp effect, is a building magnetic field. We want to see a ramp when you see a fuel injector. Called current ramping for a reason. That's why. Within this ramp, you'll notice, and this isn't always visible, depends on the amount of noise in the car too. Especially in these lower amperage settings, when you're under an amp, there's a lot of noise when it comes to amp probes sometimes. But you can actually see a little blip in that ramp. And actually what that is, again, is mechanical opening of the fuel injector. So that's not the closing side. Over here, we see the closing of the injector, and over here, we can see the opening of that injector. Now, I've read some books that say the pintle hump, that's what they call that, the pintle hump should occur 60% of the ramp. And I'm telling you, over the years of doing this, those humps on the ramp are everywhere. They're in different places. When I'm concerned about a pintle hump, would be if I see one that looks different from the other cylinders. So then you got to account for this too, is if it looks different, was that injector ever changed? Is that the same injector? Because even a new injector, reman or aftermarket component, can have a different position on where that hump's going to sit. But to give you an idea of what I'm talking about, how I use that, at the end of my fuel injector testing section, I have a case study on a Ford that had a really weird looking pintle hump. So in that section, I'm showing how to do a balance test. It's actually in section 18. We'll be getting to it next. Showing how to do a balance test, but I had one with a flow problem. And what I did is I plugged in a waveform to show you the pintle humps and how drastically different they looked with that one injector that was flowing differently. So we can use them as a guide, but you can't put a number in where that hump's going to occur. So we have a saturated switch. We let it go full ground the whole time. No limit in the driver. We shut it off. That's where we get our spike. No coincidence, at the same time we drop off our current flow. That's what a current ramp pattern should look like. Okay, voltage waveform in red, current waveform in blue. Next page, peak and hold. I have to be honest with you, I don't see these too often anymore. I have to say that the throttle body fuel injected engines all use the peak and hold injector. The GM CPI, that central port injection, the early design with the one injector, not the later design with multiple injectors, but the central port injected system GM used had the peak and hold injector in it. So you would see something like this. This waveform is actually taken off of a TBI, a GM TBI system, a dual point TBI that had two injectors. That's what this picture was taken off of. I think. I can't remember. It could have been a Dodge Omni too, early TBI. I didn't have too many of them, but this is what they look like. Same kind of characteristics, voltage waveform up top in the red, current waveform at the bottom in blue. You can see the difference in the amp scales for this, and this is what I should have picked on the last one. So instead of doing the 100 millivolt for 1 amp conversion. So keep in mind as you guys go through my book that any of my amp probe pictures that you see, that is the conversion for them. If I didn't have it marked already, 100 millivolts is 1 amp. Okay. In other pictures, this is much better. You see my amperage scale is set up already, so the scope does the calculations for you, basically. And you can see clearly that this peak is over 4 amps, just over 4, and I have about a 1 amp hold. So numbers you want to remember, saturated switch fuel injector generally draws around 1 amp of current, where a peak and hold injector is going to be 4 amps on the peak and 1 amp on the hold. Those will be numbers you want to remember. But the same characteristics, we have our off section up here so we can see battery voltage. Something interesting in this waveform, I wanted to point it out because you will see it on cars, is, and my black arrow is kind of interfering with that, but you see some hash in the voltage waveform right here, and we actually see an upside down inverted coil current ramp pattern right there. What you need to understand is a lot of our vehicles share power feeds between the ignition coil and the fuel injectors, and what you are seeing is feedback into that injector circuit. It's completely normal. It's supposed to be there. A lot of guys will look at that and think there's a problem in the injector circuit, not understanding that a collapse of a primary magnetic field where you have 300, 400 volt spikes in the primary, you're going to get some feedback into that injector circuit. When that can be crazy is at higher RPMs, and when you're looking at multiple waveforms, sometimes this spike can end up being inside of this pattern, depending on RPM. And if you're looking at all of them or only one of them, and man, can that throw you off, because now you've got this weird waveform within your waveform. You just need to understand that you have a voltage spike from that ignition coil that's being shared with that fuel injector. So you got a coil firing in a different place for a different cylinder. At the same time, you have a injector firing for a different cylinder that isn't on its compression stroke yet. It's on its intake stroke, and they can end up being the same. So look for that. Be careful with those spikes. Transistor on. Nice clean line. Notice that my ground voltage is higher on this one. I've read a lot of explanations on why that is. Just let's put it this way. There's a lot of amperage on that ground compared to the other injector, isn't there? And I think about it like this. When we talk about sensor grounds, I always give you a number, 100 millivolts or less for a sensor ground. And the reason I give you that number is sensor grounds, they don't carry any measurable amount of current flow. You're talking about microamps of current on a sensor ground. So what you can think about is that ground really being loaded with current and heat? And the answer is no. So your voltage is going to be much, much lower on low amperage circuits when you're talking about ground voltage. The higher the amperage you go on a circuit, the higher your ground voltage is going to be. Fuel pump grounds, 400, 500 millivolts is not uncommon on a fuel pump ground because you're talking 10 amps of current flow on some of those. Take our last picture was our saturated switch injector, and it was only drawing 1 amp, as opposed to this one in this peak section drawing 4 amps. Does it make sense that that ground's carrying a little bit more load and it's probably heating up the circuit a little bit more with that kind of current, and we're getting a rise in our ground voltage for that reason? You will see that characteristic on peak and hold injectors. It's just higher current flow. That's still a good ground. You know, really, as noted by the height of this peak section, that's where when we turn this on, we're giving this thing a full ground, not limiting it at all. It's a full ground during the peak section. That's why our amperage jumps so high. At that point, you see a voltage spike because what happens, the transistor switched what it was doing, and it's now limiting the current flow. And so if we're going to limit the current flow, we're going to get a magnetic field collapse. It's not a full collapse, but it's enough of a collapse to give me a pretty big voltage spike, and that's what's causing this. And of course, we have a Zener dumping this one off at 35 volts. But the injector's still spraying. So your on time, if you look at this, your on time's from here to here, pulse width. So what we see for the remainder is this hold section right here. The injector is still on. It looks like it returned to battery voltage, but it didn't. It's actually a few volts below battery voltage. 1 or 2 volts below battery voltage during that hold section. So if that's a ground side switch circuit, and it is, we could say that here in the peak time we have a full ground, and we could say in the hold time that we have a partial ground. The computer added resistance to the ground, right, which made the voltage rise on that ground circuit. You could also say that this is an intentional bad ground. That's what a bad ground would look like if we didn't want it to be that high of voltage. It's an intentional poor ground. That's how we're limiting the current flow with this fuel injector. Peak and hold. All right, what would a longer pulse width look like? I missed that. Let's go back a page. What would a longer pulse width look like here? It would simply be a ramp, right, that would extend, and a voltage waveform that would extend. So this is what your longer on time would look like. Just the waveform opens up. What would a longer pulse width look like on a peak and hold is only this section increases. And what would happen in here is the two spikes will separate themselves. So the peak time is the time that it takes to build the magnetic field and open the fuel injector. That doesn't change, stays the same. But when we change the pulse width, What we change is the hold time. That would be a small pulse width, and this would be a very large, long pulse width. The hold time. So the two spikes will separate from each other. If you do a snap throttle test and you're watching this, that's what you would see. The only time that you would see the hold section change, the peak section, there is a time that you'll see variations in the peak, and it's during cranking. When we're cranking, the peak time will be longer because battery voltage is lower. So they'll increase the peak time to get that injector to open up real fast. If you ever did one, experiment with it, play around with it, check it out during cranking, take some measurements, and then check it out with it running, do some snap throttle. You'll notice with the engine running, our peak time never changes. The only time peak time changes is when we have battery voltage changes. And that would be cranking in this case. So peak and hold, peak current, hold the current. It's about controlling the temperature of the winding. If we kept it at 4 amps the whole time, we burn up the injector winding. You won't see too many of these, but they're still out there, and they're going to be good to talk about it. We still have our characteristic of our pintle hump right here. So we got a little hump right there, and it is visible. I have a case study of this in the next chapter. We'll get to it. I have a case study of a peak and hold injector where it's stuck closed, and I'm showing you these waveforms with it sticking closed. Somewhere within this current ramp is the opening time of the fuel injector. It's not really visible, and I'm pointing that out in this case study. I have a couple zoomed in pictures of a stuck closed one, and what I did is I showed you a zoomed out picture like this, and then what I did is I zoomed in on this side and I zoomed in on this, and I showed you the characteristics and what we're looking for a sticking fuel injector on a peak and hold. That's in section 18, one of the case studies I have in there. And this is just a review of what we talked about. Peak and hold driver, you guys can read that on your own, and saturated switch driver, and it's the same information that we just talked about. So this should give you a real good heads up on what we're looking for when it comes to injector waveform diagnosis. Question I wanted to address is the Honda version, and the question was, where is the resistor for the Hondas? Is it part of the injector? And the answer is no. It would be a remotely mounted resistor block of some type away from the fuel injectors is what you'd look for the series resistor injectors for the Honda design. So that's it. Injector designs. Next thing we're going to be doing is injector testing, section 18. In section 18, we're going to be talking about all the injector tests that are available to us, how to use them, how to do a sound test. What are your variables with a sound test? How to do a Noid light test. How to determine if the light's on all the time or if it's flickering or not on, what your causes are. Also, of course, injector current and voltage waveforms. We're going to review what we just talked about. And I have a whole bunch of case studies, shorted injectors, stuck injectors, voltage waveforms, current waveforms that aren't right, to just emphasize what we look for when we do fuel injector current ramping and voltage waveform testing. Section 18 coming up next.